Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 3, Topic 2. Exploring Conduction in Semiconductor Packaging, Understanding Fourier's Equation and Thermal Resistance Equations. Introduction. In the intricate realm of semiconductor packaging, the efficient management of heat is indispensable for ensuring the reliability, performance, and longevity of electronic devices. Conduction, one of the primary mechanisms of heat transfer, plays a pivotal role in dissipating heat generated by integrated circuits within semiconductor packages. This overview delves into the fundamental principles of conduction, elucidating Fourier's equation and thermal resistance equations, and exploring their significance in semiconductor packaging. Fundamentals of conduction. Conduction is the process by which heat is transferred through a medium or between different materials in direct contact, primarily driven by temperature differentials. According to Fourier's law of heat conduction, the rate of heat transfer through a material is proportional to the temperature gradient and the thermal conductivity of the material. Mathematically, Fourier's equation is expressed as Q equals minus K dt, dx, where 1. Q is the heat flux, W per square meter. 2. K is the thermal conductivity, W per meter K. 3. dt, dx is the temperature gradient, K per meter. The negative sign indicates that heat flows from regions of higher temperature to regions of lower temperature. Understanding thermal resistance. Thermal resistance quantifies the resistance to heat flow offered by a material or structure and is analogous to electrical resistance. In semiconductor packaging, thermal resistance plays a crucial role in characterizing the thermal performance of materials, interfaces, and package configurations. The thermal resistance R of a material or structure is defined as the temperature difference delta T across it per unit heat flux Q, expressed as R equals delta T, Q. In steady-state conditions, the total thermal resistance of a semiconductor package can be expressed as the sum of individual resistances across different components, including die-attached materials, package substrates, interconnects, and thermal interfaces. Thermal resistance equation. The thermal resistance R of a material or structure can be calculated using the following equation. R equals L, K dot operator A, where 1. L is the thickness of the material, m. 2. K is the thermal conductivity of the material, W per meter K. 3. A is the cross-sectional area of heat flow, m squared. The thermal resistance equation demonstrates that thermal resistance is inversely proportional to the thermal conductivity of the material and directly proportional to its thickness and the cross-sectional area of heat flow. Materials with higher thermal conductivity offer lower thermal resistance, facilitating more efficient heat transfer. Application in semiconductor packaging. In semiconductor packaging, understanding Fourier's equation and thermal resistance equations is essential for optimizing thermal management strategies and mitigating thermal issues. By quantifying thermal conductivity and thermal resistance across different materials and structures, engineers can identify potential bottlenecks in heat transfer and design package configurations that minimize thermal resistance and maximize heat dissipation. Die-attached materials. Die-attached materials, such as conductive adhesives or solders, play a crucial role in facilitating heat transfer from the active semiconductor device to the package substrate. By selecting die-attached materials with higher thermal conductivity and minimizing their thickness, engineers can reduce thermal resistance and improve heat dissipation efficiency. Package substrates. The thermal conductivity of package substrates, typically composed of materials such as ceramics or epoxy resins, influences the overall thermal performance of semiconductor packages. By optimizing substrate thickness and selecting materials with higher thermal conductivity, engineers can minimize thermal resistance and enhance heat transfer capabilities. Interconnects. Interconnects, such as wire bonds or solder joints, provide electrical connections between different components within the semiconductor package. However, they also contribute to thermal resistance and may impede heat transfer if not optimized. By minimizing the length and cross-sectional area of interconnects and selecting materials with higher thermal conductivity, engineers can reduce thermal resistance and improve thermal performance. Thermal interfaces. Thermal interfaces, such as thermal interface materials, TIMs, are used to improve thermal coupling between different components within the semiconductor package, such as the die and heatsink. By selecting TIMs with appropriate thermal conductivity and optimizing interface thickness, engineers can minimize interfacial thermal resistance and enhance heat transfer efficiency. Conclusion. In conclusion, Fourier's equation and thermal resistance equations provide fundamental insights into the principles of conduction and thermal management in semiconductor packaging. By understanding these equations and their applications, engineers can design semiconductor packages that optimize heat transfer, minimize thermal resistance, and ensure the reliability and performance of electronic devices. As semiconductor technology continues to advance, mastering conduction principles remains a critical imperative for sustaining progress and driving innovation in electronic packaging.